Housekeeping. Lunch will be here at 11:15. It will be delivered back there. So as soon as Joseph is done, we should be ready to go. At least that's what he's promised. Gotti apologizes that the Wi-Fi sucks, and I'm certain that if you just email him directly and tell him how terrible it is, he will feel even worse. So I recommend you do that. Otherwise, this is the last talk before lunch. Please feel free to wander off if what comes does not suit you. The entire point of this is community, so I would encourage you to grab a stranger, go grab a taco, do whatever it is you guys want to do and talk, and then come on back and bring back the ideas. So without further ado, here comes Joseph, and I'll let him introduce himself. Thanks a lot.
Hello. Can you guys hear me okay? Yeah. All right. Today we're going to be talking about some research I've been doing the last few years, particularly at the startup I'm at now called JASK. And this is just all about kind of enhancing SOC workflows through sort of a couple key technologies. One is cloud, and two is more generally pattern recognition systems and sort of certain types of artificial intelligence that we call reinforcement learning. That's kind of helpful in certain corner cases and use cases around just SOC operations. I think kind of like to just sort of frame how I kind of got into this type of research topic and kind of where, speaking the security operations and security research, really there's just like quite a bit of verbiage that's spoken across a couple different technology stacks. I end up speaking computer science, a little bit of statistics, the vernacular, the OSI model, talking about just all these different technologies, and I think kind of where I sort of got the color to kind of speak some of this verbiage is I originally got into computer hacking when I was just learning tutorials on cracking passwords. So the first hash I ever cracked was with like John the Ripper and some of these old tools back in the 90s. And I ended up going to a couple DEF CONs. The first DEF CON I went to was DEF CON 8. And I saw some talks there that kind of sent me down a rabbit hole where I went to grad school. I studied math in college. And I was really just trying to understand like these things they showed at DEF CON, like this talk we went to was on Shor's algorithm and how you could break RSA on a quantum computer. And it was just this really kind of beautiful synthesis of like science and technology. And I've kind of been, I've just sort of been a researcher ever since. And so I spent a long time in college at the same time as working as a help desk and support engineer for like a telecommunication operation. And I learned a lot of like, that's kind of where I did the original data science for telecommunication networks, as I was building like old network management systems with SNMP, technologies called Armon. And I eventually sort of used that knowledge once I got out of grad school kind of in present day cybersecurity modeling. And I've just been sort of, since I got out of grad school, I've been at a lot of like startups and just consultancies for data science. And there's a ton of projects that are really fun in this space. But for what's really important for me, and one of the reasons I'm kind of at the startup I'm at now called JASK is I really think it's part of the hacker spirit to try to share as much knowledge as possible, to try to open source as much techniques as we can. And for security, when we do data science, what is really lacking in this problem space is data that is available for making kind of robust conclusions on. So a lot of the projects, I mean, we'll kind of show this in the appendix, but this is just sort of a real quick cliff notes of some data sets we try to open source and just champion kind of evangelizing, sharing ideas and knowledge at a grassroots level. Okay, so kind of getting into this sort of conversation of what does it mean to kind of accelerate the SOC with cloud workflows. Part of what we're going to be talking about is like how do we like efficiently train pattern recognition systems and encode in our security workflows metadata and a schema that software systems can learn from and pick up kind of operator knowledge and patterns. And I'm just going to kind of sort of frame kind of what that workflow really means in the present day. And I'm borrowing a couple of slides from our CTO who really, I love the way he sort of kind of categorizes this problem. Today's sort of modern SOC is kind of, the analyst lives at the SEM console. And in a security operations workflow, in a large 24/7 operation, there's just this kind of, the approximate breakdown is get a new alert, prioritize it, and get context for that alert, and either mark it as good or bad. This job is tough. Doing security at scale in a security operations center where you have like a large SEM in the Fortune 500 or the Fortune 10 space, users, you're talking about hundreds of thousands of users that generate potentially billions of alerts. And it's this classic kind of cliche needle in a haystack problem that the bigger the environment, the more users we're sort of protecting, the lower our efficacy goes as human, the worse our efficacy gets as operators. And kind of part of why that workflow is challenging is there's sort of a lot of kind of statistical inference that's baked in under the hood. Like when we get a new alert and we sort of have to prioritize and kind of correlate and mix all the state related to this alert, what we're really doing is kind of building in this picture of reviewing context, making correlations, and using these usually event log sources that are kind of representing state at a particular point in time. And kind of all that stuff is sort of mixing together in an analyst workflow or sort of a decision tree-like process. And typically, like not all these systems are like talking the same language. So the analyst sort of has to normalize some data, figure out which IP address was associated with a MAC address at which time, and just correlate and like navigate through all the metadata that kind of exists in modern sensors. And so this sort of workflow in the SOC kind of just creates a ton of challenges. Some of them are just sort of kind of the inference problem is one of the biggest ones. And just being able to connect the dots in the right way, but also humans can only keep like a certain number of working items in memory. You know, we have a small buffer, so Miller's Law comes into play. The timeliness of these problems in the SOC. There's always a fire drill related to security events, and there's a lot of challenges that sort of permeate a SOC workflow. Alongside just those classic kind of like examples that I think anyone who works in the SOC is familiar with, we have sort of these more kind of theoretical anecdotes. One of my favorite one is from Mudge from Loft and later at DARPA. This is pretty like classic canon in a sort of black hat and just different presentations. I think we could even get this from the Malware Analyst Cookbook, but basically there's a section at the beginning of the Malware Analyst Cookbook that has this little breakdown on this DARPA study. And what DARPA did was they analyzed a few thousand samples of weaponized code, a bunch of malware that had been targeting like DoD systems and stuff. And they sort of compared and contrasted what it means to look at kind of the resource profile. This was sort of a proxy for measuring like what it means for an attacker to spend resources weaponizing a piece of code versus what it means for defenders to sort of spend resources. And I think this is a good, I mean, you can kind of critique this metric, but I think what's really nice about this as kind of an approximate and just getting the conversation started is that for an average, Mudge used this example. They had a 150 line PHP malware that, you know, it was weaponized, it was malicious with just 150 lines of code. And the average antivirus product that was defending against that was 1 million lines of code. So this is kind of a classic resource imbalance problem if we kind of step back and think about just the posture of defense and strategy. And this is what we call sort of an asymmetric warfare situation where the cost of playing defense is exponentially higher than the cost of playing offense. And this will kind of go into some of the themes and the constraints of kind of what we talk about today. And so I think when I kind of think about all these challenges and problems, like from a researcher perspective, I mean, this is a really fun problem space for me to think about because it kind of begs the question of some sort of deeper philosophical underpinnings. And one of them I think about a lot is like if I like how do I say it best? So like artificial intelligence is kind of like an overloaded operator right now, especially in Silicon Valley. We see it thrown around all the time. in my mind, it's as a researcher, it's a tool that solves a special class of problems. That class of problems is about pattern recognition. And not all patterns are created equal. So some patterns are extremely complex. The weather's a good example. Another pattern that is really, really complicated is something that has to do with kind of adversarial problems. And basically, that's a synonym for saying that there's certain patterns that are going to change and be limited over time. So I think in this context, can we use these software systems, can we use the cloud and some notion of machine learning to help us deal with problem spaces where we have to predict adversarially generated patterns or patterns that change over time? And in my experience, the answer is in the bigger philosophical kind of framing of the question is there's certain problems that artificial intelligence isn't going to solve anytime soon. I think this is, and we'll kind of touch on a little anecdote shortly, but like there's these huge breakthroughs in AlphaGo. Hopefully everyone's kind of gotten to hear some of like the interesting results related to like the deep neural network systems beating like the world's greatest Go players. There's been a whole advance lately, partially because of the commoditization of compute and the cloud, partially because of new algorithms, but also kind of what happens under the hood is the problems that these artificial intelligence systems are really good at are sort of discrete in nature, and they're not general enough to deal with sort of the full kind of breadth of sort of a sophisticated adversary. So kind of one anecdote, and we'll mention this again in a second, the actual papers, but where Google DeepMind is really struggling right now is predicting StarCraft games. So it's beating the world-class Go player because that's kind of a discrete search space. But when we move to sort of a continuous space of behaviors and actions, the DeepMind is no better than a novice StarCraft player. And I think there's a bigger question that, I mean, this is just empirical observation, but there's certain problems that we as kind of just living, breathing wetware have encoded in our DNA and in our computation that's about sort of survival instinct. We have sort of the ability to do pattern recognition for survival at a scale that I personally believe theoretically that there's limits that computers won't be able to beat. But that's kind of getting into the philosophy of things. I think more than anything, kind of where I've kind of seen this happen empirically is just whenever we work on a problem where we have to sort of break the problem space down in sort of an adversarial model, and then kind of on the y-axis think about as the sophistication of the adversary increases, what are sort of the tactical use cases and kind of software-based solutions I can find that help me detect this threat actor. And so as we kind of try to get more expressive with the techniques for detection, the overall efficacy in my experience of tools like pattern recognition and machine learning kind of go down or decrease in overall effectiveness, because by definition, like advanced actors are going to do the most to change their patterns and not fit a baseline profile like hitting old IOCs or executing a type of exfiltration that's been seen in a previous campaign. So I think part of this problem space is there's a non-equilibrium that's achieved because the whole point of the adversary is to make themselves unpredictable in certain ways. And so I think really thinking about how I break down the model of an adversary as a researcher kind of makes me sort of think about these bigger problems and like what are really the limits of machine intelligence. But that's kind of just a little bit of a tangent. I think kind of to sort of recenter here and think about like the conversation of how can these tools and particularly machine learning help us in the context of defense, given that certain problems, the problem of adapting to an adversary's changing patterns are really hard in general, how can we sort of effectively optimize the use of kind of state-of-the-art technology and things like pattern recognition to help defense? And I think one super simple experiment, this was kind of the meat of the abstract for this talk, was just about talking about how, particularly the last couple of years, the systems I've been working on have leveraged the cloud to propagate operator feedback. And so what that really means in a very simple kind of sort of embarrassingly parallel type of problem is just like leveraging a schema and just sort of open threat models to communicate what operators do in triaging and investigation, and in a way that what happens is we don't want to just share, okay, this IP address is bad or good. We don't just want to share indicators of compromise and sort of just classic signatures. But what we end up doing in this sort of cloud-enabled AI workflow is sharing and creating this process of analytics through tagging all the data that's both good or bad for a particular IP address that was investigated. So we create kind of a neighborhood of context that lets the machine see both normal and malicious behavior. And then we also kind of pass the algorithms and some of the other things that are able to build kind of higher level detections and semantics for these pattern recognition systems. I think the second part of kind of how we leverage the cloud in this conversation in defense, and this is really where I end up engaging like kind of more mature enterprise customers who have usually kind of been thinking about data science and analytics for a while. But what we end up really talking about for a security operations center is how can we best affect and establish a culture of machine learning in SOC workflows. And what this really means is, like in security, analytics is kind of a relatively new topic. Like in certain problem spaces, like in Google search, for instance, or clickstream prediction, the problem space is much more narrow, and the industry as a culture has had a long time to kind of process and assimilate these ideas. In security operations, we're really we're really in our infancy in talking about what it really means to sort of affect this culture. And I think hopefully that will be one of the big takeaways I walk you through in a second, is kind of like, what does it mean to sort of establish a process-based workflow that really lets us transfer operator knowledge from security operations into sort of a schema and into a set of data that pattern recognition systems learn from. And I think kind of what we're going to see as a consequence of, if we do this correctly, what we end up doing is we're building kind of a rich vernacular, or what we call in these slides like a behavioral taxonomy that is really meant for our pattern recognition systems to be expressive and to describe lots of context. Two of my favorite kind of like, I've sort of been kind of a little bit of sort of having the framing of a lot of constraints in this first set of slides, and I think one of the ways we can kind of justify some of these just problems we see with pattern recognition, machine learning, and data mining in cybersecurity is, there's a couple talks that I'd really recommend checking out if you want to kind of get into the meat of this. And these are some of the Google researchers who spend a lot of time mining cybersecurity events at scales that most other enterprises, besides like Baidu and companies like that, could not even imagine. And so I think this is kind of just getting back to what I just kind of like to sort of rephrase and just want to make sure everyone kind of understands is in what we're going to show next is how we train one of these systems in the cloud. Well, what we're really kind of doing is we're trying to kind of put forth an idea that's more than just an algorithm. It's about like, how do we affect a culture of machine learning and security operations? And I guess one way to sort of think about this a different way is, and I love this kind of this quote in as sort of a general kind of data point and how important like the process-based workflows for analytics are. And so this is a professor of distinguished. He's a distinguished professor of electrical engineering, chemistry, and statistics at Berkeley. He's a famous machine learning researcher named Michael Jordan, and And he did this Ask Me Anything on Reddit a while ago, and it's a cool Reddit. It's just fun. Like he recommends books and his favorite machine learning topics. But one of my favorite questions of all time is someone asked him, if you had $1 billion to spend on a huge artificial intelligence project, what would you do? And like his answer is, I would invest in human-intensive labeling processes. And this is kind of where I want to just beat to death this concept of affecting a culture, machine learning, and the SOC. It's synonymous with this answer. Invest in human-intensive labeling processes. And hopefully, this is where we're going to kind of get into a little bit more, I don't know, just technical illustrations of what this means. So what does it mean? I mean, you've probably all done this either in kind of in one form or another, in some stats class or biology or anything if you haven't done security. But what happens is in building pattern recognition systems, sometimes we call this truthing the data. But what happens is in security outcomes, usually we'll get a set of evidences. This is sort of a bad approximation. I basically took a bunch of alerts from a SOC system and stuck them in a table and counted like key fields of evidence. But this is just, think of this as kind of like a generic roll-up for incidences related to domains. Like basically the operator is analyzing when a domain is either serving malware or when it's just benign. And what happens is a typical operator will kind of label and triage the output associated to each one of these events based off other alerts, some other factors. Sometimes they compute just IOCs and bounce threat intel telemetry off the domains. But eventually what happens is the operator will sort of label either malicious or benign in terms of the outcomes associated with these events. And if we don't have like an upstream system that can process this, this is about all that happens when the operator is done labeling. They'll close the event, they'll wipe the machine, and kind of the escalation is contained. But if we sort of start kind of taking that idea of labeling, where now I sort of have another column in a data set that's just is much more generic and has nothing to do with security, but this is just sort of an open source data set related to cars. And one of the things we had a human label in this data set was the miles per gallon associated to every car in our data set. And what we're going to kind of walk through is what do these pattern recognition systems really do when they're making a prediction given some human input? So here's sort of our blue column is the human input. And what we're going to do is we're going to fit like the simplest model possible. This is what do we call this? A linear regression or a linear model. And kind of how we're building it is we're using a program called R, and we're just fitting this model using a hypothesis that says our miles per gallon is proportional. Oh, and you know what? I messed up the syntax here. It should say weight, displacement, and like the number of cylinders. But basically, this model is just taking a couple of field names from kind of our dependent variables and predicting kind of an independent variable is sometimes how the syntax works. And I think the key idea in understanding what's really happening in these artificial intelligence systems is when we run our model, what we really output is a piece of information that's very useful for describing or hashing the input data. And so this kind of gets into the philosophy of learning. So when we learn something, it could be a software system, it could be our own wetware. Our brain does this too. When we learn something, we compress the information and we encode a meaningful representation that is used for certain things. Like in this case, what I've taken with a machine learning algorithm is a data set, and I returned a line. What I really returned is the coefficients that describe a line. But now, anytime I need to make a new prediction involving this data set, what I do is I just read off where the data will file on that line. So I don't need this huge piece of information anymore. I have a compression or a hash of the information. And this is really like the key kind of intuition that underpins these learning and pattern recognition systems. there's a lot more to it than just returning a set of coefficients in general. There's metadata that describe kind of how the model performs, all this extra stuff about accuracy. But in general, from a learning process perspective, when we learn something, we transform the data and we compress it. And this happens in biology, and it happens in software and hardware systems. And there's different ways to compress information. So I can learn a representation, a linear model that basically is kind of, we can think of visually as a line, or like in the hot buzzwords these days, what models that are best in breed usually are deep learning based, and they learn a much different encoding than a line. They learn sort of a representation that's sort of this picture of activated weights in this kind of directed graph. But anyway, I think that's kind of the interesting aspect of kind of the philosophy of learning and how it affects not only biological systems but software systems, and where we really see how this I like showing these slides in terms of what happens under the hood with a piece of software, piece of like artificial intelligence software particularly, is that these things are very brittle. So when I learn a pattern and then I've changed the pattern the next day, we have to re-encode and engineer a process. How do I reweigh the new data from the old data? And it's very challenging when engineering systems that adapt to change. That's why nature has given us some really just insanely valuable tools when it comes to adapting to change for survival instincts. But in any case, I think kind of going back to framing our analyst workflow. So now when we use the SOC for when we enhance the SOC with these pattern recognition systems to sort of assist this operator process, what we end up doing now is kind of having this third checkpoint, this last checkpoint, that is kind of a machine learning validation step. And that's really where I've kind of built some of the statistics about what is effective given a certain number of customers. It's kind of building this workflow in and assigning a little bit broader of a definition of what it means to validate evil versus just good old-fashioned normal traffic. So we kind of repurposed the idea of signature a little. I'll show you what that means more like in a concrete term. But I think a signature in our context, when we have machine learning kind of helping us, is any algorithm we're using for detection. So by definition, an indicator of compromise falls into this, because an indicator of compromise is sort of just more or less just a Boolean pattern match, or a very simple type of algorithm. But basically what happens is we have a very kind of rich data structure that describes how we did detections that's more expressive than just having to look for a specific IP address or an MD5, alongside a mechanism and more of a process-based workflow that lets us propagate information through sort of our cloud instances, or our more or less our architecture, in a way that lets us share data that is important for kind of automating these predictions in the future. And so here's an example of what I mean by like algorithms as signatures. This is part of some of the GitHub code we shared when we have a project we showed where we're basically training a random forest on detecting the delivery of a payload from just in HTTP logs. And so what we have was about 300 or 400 samples of exploit kits being run on just websites and watering holes, and kind of these attacks where a user clicks on a malicious iframe or some type of redirect, and they're eventually served a payload. And what we kind of did to study that problem, I mean, we used normal indicators of compromise. We didn't want to throw anything out, but we also kind of built into our taxonomy. It's kind of like looking at a spreadsheet where for each user you have kind of like all the IOCs, all the known snort rolls they hit, plus like a little bit more expressive of statistics that some of them are really benign. Like a lot of the statistics we found that were useful had to do with the timing, the encoding of the timing. But like in my experience, I mean, it's sort of silly. It's like a configuration file that describes some additional statistics besides the IOCs. But in my experience, even in really large-scale operations, this kind of tribal knowledge that an operator will like write a Splunk rule for or build a SQL query for is lost in upstream analytics. I've talked to very few customers who are kind of have a sophisticated enough kind of analytics workflow where they pass the metadata and kind of the thought processes in the playbooks along with their outcomes. And so I think it's just sort of like to plant the seed is you don't just have to pass the outcomes. You can kind of get meta about it and pass the algorithms that were used. And I think when we see in security how important it is to adapt to changes, the more we can kind of pass the underlying technique and commoditize the techniques and the algorithms that we're using for defense, the closer we'll get to this kind of this threshold of being able to rapidly adapt and spread information through the cloud. I think we got like a few more minutes. I just kind of wanted to touch on before maybe we got to questions.
Before you move on, real quick,
Yeah.
are you using the metadata to sort of age, like you're saying the signature is the algorithm, are you using that to sort of age your algorithm? Like, oh, this one's no longer effective, it's time to move it on?
Yeah, so that's a really good question. The question was, like, are we using data and metadata to age our algorithms? And I think that is, I don't have the slide there. I'll show you the GitHub link at the end where we have documentation on basically another PowerPoint deck we did a while ago at Black Hat or something, where we really talk about what does it mean to engineer a system that learns over time. And the three key questions you have to answer from like an API perspective is how do we weigh new events over old events? How do we decide if we need to forget? And it kind of becomes a case-by-case basis. That's exactly why we, like, for certain use cases, it's kind of clear, and for certain use cases, it's not really like worth even attacking. So I kind of take it as a case-by-case basis. But if you're interested, I'll point you to some links where there's a little bit more kind of like literature about that problem. And I think kind of going into like what does it mean to build a system that learns over time, kind of touching on that point in a different way is just mentioning, sorry, real quick, I just want to mention, and this is a kind of another common buzzword, particularly with the AlphaGo problems. They were leveraging reinforcement learning a lot in a little bit different of a way, but kind of from a high level perspective, what we're going to be talking about is leveraging the type of techniques in machine learning that allow machines and software agents to automatically determine the ideal behavior within a given context in order to maximize performance. Where word feedback and a feedback loop is required for these type of techniques, and this reinforcement signal is usually built through some. It's not just algorithms. It's a really smart design of human-computer interaction. So HCI is part of what kind of makes this magic stick. And I think when we sort of think about these systems really quickly and naively, what happens is there's a few different types of ways where we can kind of teach pattern recognition systems to learn from expert feedback. One way, this is the unsupervised case, is if we don't have an operator dealing with the data ahead of time, and we just sort of input it, process the output of the algorithms in a sort of a very naive workflow. The second case is the case we kind of saw in the slides where we were labeling a little bit of data. This is called like vanilla supervised learning sometimes. And then the final case, I guess there's two cases rolled up into here. Sometimes C is called semi-supervised learning, but it just means we're kind of starting from a small amount of information that is labeled. And the case that I think is most important is in this broad context where we leverage these cloud workflows is multi-intelligence fusion reinforcement learning. This is critical to training artificial intelligent real-world systems that have the following characteristics: minimal amount of labeled data for items of interest, inconsistent and changing nominal environment, and most importantly, adversarial scenarios in which targets employ deception and obfuscation to hide in nominal data. And this is sort of our tool we leverage that is kind of inspired from some of these latest breakthroughs in science. So this idea of kind of getting feedback and tuning a system over time is one of the ideas that led to the AlphaGo breakthrough. But even here, we hit some constraints, and that's why I think it was just important to mention, if you're not aware of it, there's another paper that's kind of related to the AlphaGo results, and it's asking now, can we do the same type of artificial intelligence and adversarial modeling in a space of kind of continuous transactions or continuous behaviors? And it turns out for StarCraft 2, artificial intelligence is just failing. And part of it is because the search space, the degrees of freedom are in such a higher dimension than sort of a discrete game. I think we got about 4 minutes left. I think kind of what I just really quickly want to show you is sort of like, so kind of given all those limits, and even when we have the limits of reinforcement learning, kind of given the StarCraft results, like how do we mine an infinite search space of behaviors where we have a lack of labeled large quantities? And I think kind of the results of some of the experiments we've done at scale with large amounts of kind of shared information is there's these layers of accuracy. When you only have a small number of people in the cloud, basically you don't need machine learning. We can just leverage heuristics and cloud search population to kind of tell us where we're at. And eventually, when we kind of get to a certain critical mass, we can turn these techniques on that are a little bit more robust and are basically at a certain point going to beat and outperform the humans. There's sort of another part that I kind of want to get into. This is a little bit theoretical, and it's just how we leverage like MITRE, the attack frameworks, and some of the cooler kind of math involved in describing the semantic hierarchy and kind of propagating that information back. But I'll stick these slides online, and if you guys want to just come talk to me afterward. Oh, sweet. Okay, yeah. No, I think I got my card. Come talk to me afterward if you got a lot of questions. But yeah, can we?
Okay. First question. So, like going into the StarCraft example, for example, you're talking about like, hey, the attack space is a really unconstrained environment. Have you looked at a way of trying to introduce constraint by identifying threat behavior or threat intention? So, for example, you have the entire corpus of the attack surface. Well, what if I only want to focus on these are the steps required, or this is what characterizes a ransomware attack, or a entrenchment event, or some other, like the attack framework, for example, a portion thereof, and then design your analytics around that instead of having to try and train something to capture the entire corpus of possible events. Does that make sense?
Yeah, 100%. I think you're touching on sort of the dark art of doing this modeling and being effective at it. Usually, and I kind of come into cybersecurity modeling from a consultant perspective, so the way I'd always see a problem is sort of breaking the threat surface down into some actionable use cases. And typically, when you talk to like an actual customer who's spending money on this, there's a set of use cases they don't have good coverage for from their point solutions. That's typically where we, like ransomware is a great problem where I've spent a lot of time where you can kind of dissect the binaries associated with ransomware, dissect like the callbacks, and just spend some time saying, like, what is typical of these patterns and what is invariant? It turned out ransomware didn't, like we were used to using techniques that were more vanilla command and control based detecting covert channels, but ransomware doesn't need to phone home after it sends its encryption key. So we kind of started thinking more about that problem from what does the initial exploit look like? Like how does payload delivery happen? And we have sort of a GitHub, let me kind of just pull up these. But basically, yeah, this was actually kind of one of the ways we're sort of targeting just the ransomware problem is at a high level that use case, kind of we associate a set of statistics that were related and dependent. And I think when we kind of model these things in a proper abstraction, this kind of comes from the Bayesian modeling kind of family techniques. When we model like a particular use case, the features are statistically dependent. That's kind of how we know we've built a kind of a proper abstraction for relating some of these ideas. And so I think it's So just kind of to touch on this ransomware topic a little bit more, like these two projects that are in blue are kind of where we kind of go in depth in how we built a machine learning model that's targeting the ransomware problem, and particularly how exploits are delivered in that part of the attack stages, I guess. That help answer the question? Good? All right, sweet.